So we're here at the lab in Hawthorne, New Jersey, and I have a mobile camera that I use to allow us to show us around the lab. And let me show you guys what it is we are doing over here. Jeremiah is working on some stuff on the board, but this is a lab space that we recently just set up. This is in addition to the Faraday cage and the control room we have out on the other side of the lab. There's a bit of construction going on over there. We're renovating the bathroom and some other stuff. I'm not going to join with audio on this one. This is pretty much our lab setup. We have the gyroscopes. Right now we only have one gyroscope. This is for the gyroscope precession experiment. They're coming in from the United Kingdom, from Great Britain. It should be here sometime later next week. And we're also working on Alzofon, which is the dynamic nuclear orientation experiment. We have two systems to run this experiment. Basically, it's a laminar magnetic field, similar to what Todd was talking about. You need to create a laminar homogeneous magnetic field, and then you hit it with microwaves at the Larmor precessional frequency. And it's all laid out in the book over here, the paper written by Frederick Alzofon. I've gone over this a couple of times at APEC. Antigravity present technology. This was actually published in 1981, and they replicated the experiment in 1994, apparently, with 80% weight loss within the first second. So I thought it was a pretty promising experiment to try. It does have a very high benchmark to enter this experiment because you need a microwave source, and it needs to be coherent microwave source. So it's kind of hard to just use a regular microwave generator. We're using a traveling wave tube. We also have a klystron that's capable of 3,500 watts. The traveling wave tube is only capable of 20 watts. We're having trouble with the waveguides in order to get all the energy into the test sample. This is pretty much laid out over here. This is the waveguide. I'm sure it doesn't look like this exactly. And you have the north and south pole of the electromagnet or whatever magnet you are using. And what that's supposed to do is create a state of dynamic nuclear orientation where the nucleus of the atom is actually oriented, and that should detach yourself from the Earth's gravitic field and possibly the inertial field. There's a couple different explanations to how this experiment would work, if it is successful. So there's more theories than there are experiments in this regard. We've also worked extensively with Thomas Townsend Brown's work with the gravitator. He calls this the Byfield-Brown effect. Really, it's all about Thomas Townsend Brown. This is actually the only paper where Byfield is mentioned. And so far, our replications have had mixed results. We had one guy in Vietnam, Nam Tran, who tried these experiments. He's always getting positive results, and then he sent over his capacitors to us to try them, and we were getting null results using our DC power supply. And we since realized that the power supply may be, the signal input to the parallel plate capacitor may be more important than the capacitor itself. And given the type of technology that he had at the time, it's possible that it wasn't a very clean DC signal. There might have been a DC bias with more of an AC form on top of that, or an inverted sawtooth. And that is something that we're looking into. We actually have the components to build that and try that experiment in that fashion. I don't believe this is warp drive. Right now, our current theory is that it's more of a electron rocket of some sorts. And it would create a bit of propulsion, which, when used in conjunction with the dynamic nuclear orientation experiment, which will pretty much remove all the inertial mass of the craft, you can then use a small amount of thrust to propel the craft in whatever direction it is you want to go. And that's kind of what, like, Mark McCandless's ARV picture shows, where you have the parallel plate capacitors in the base, and there's these big coils, and there's an aluminum flywheel. It's kind of important to use aluminum for this because aluminum maintains its dynamic nuclear orientation better than most materials. The way the dynamic nuclear orientation is created is by applying the homogeneous magnetic field, which, as Todd mentioned, is pretty difficult to achieve. An EPR electromagnet is, the ideal. That's what's already that's the standard approach. But those things are very big and very expensive and hard to find. We do know of one that's in South America in a dumpster that we might try to salvage, but it's been there for a couple of years, so it's probably all corroded. But these devices are pretty hard to find, so we had to build one ourselves. Then you have the sample in the center of the homogeneous magnetic field, and having a sample in the center of a homogeneous magnetic field, what that does is it orients the electrons based on the strength of the magnetic field, and they precess, which is the spin of the axis, at the Larmor precession, which is way up in the gigahertz range, which is why we have to use microwaves. So it's really about tuning the microwaves to the strength of the magnetic field and pulsing the microwaves as well, because every time you pulse the microwaves, it energizes the electrons, and then that orientation can then, when you turn off the microwave force, can then transfer its orientation to the core, and you slowly build up a orientation in the core, and basically creating nuclear magnetism, which is pretty much what this effect should be called, in my opinion. And once you have that, the craft should lose its inertial mass and detach itself from the gravitic field, because second law of thermodynamics states that everything goes toward a state of entropy, goes from order to disorder. So in the core of an atom, we can expect there to be a lot of entropy. There's all the subatomic particles are probably spinning, precessing in all different directions with very intricate spins. And it's possible that that is what creates the inertial frame in the first place, by having all these spins and these precessions and precessions of precessions. When you move an object through space-time, what you're actually doing is you're adding inertial energy to it, or kinetic energy to it. What you're actually doing is energizing the subatomic particles in the core of the atom, which is where all the mass is stored. And then when it hits, when the baseball hits the bat, all those spins all change. But if you orient all of the spins and they're no longer incoherent, you make a state of coherent matter, the craft will then essentially become weightless. And as David Alzofon stated in his book, he actually wrote a couple books on this. This is the son of the inventor, Frederick Alzofon. So this is David Alzofon's 2 books that he wrote, and they're published on Amazon. That it's also possible that this can create an invisibility system, because we're all interacting over here, like even on this table, we're interacting with the electron field. We're not interacting with the core of the atom. The core of the atom is what creates the inertial mass, but the interactions that we're having here are really with the electron field. So if you oriented all of the electron fields, it's possible that light will be able to travel straight through the hull of the craft, and that can explain many of the phenomena that I've seen around flying saucers and such. But this does not create propulsion. This just gets rid of the inertial mass, if it works. And propulsion can be created with possibly with this experiment. We're also trying the Podkletnov impulse experiment using superconductors, and that paper is over here. This is from Podkletnov. You're all very familiar with this. This is actually from Tim Ventura's American Antigravity, and they used a Marx generator similar to what we have over here, and we are trying to build a Marx generator ourselves. We have a whole bunch of capacitors, and Jeremiah can show you what we are doing with that so far.
Yeah, so we went on eBay and got a bunch of these surplus 30 kV 1000 picofarad capacitors. They're really nice and decent polypropylene capacitors, so they'll have a very low ESR because of the technology that's used, and they also have a fairly high resilience to partial overvoltages, where they can still operate even if there's a problem with one of these caps. So we got a total of 8 of these, or 10 of these boards. Each contains 8 capacitors. We were missing one. We went through and tested all of them. We found a total of 7 bad capacitors that we're not going to be using in this system. So what we ended up with is a bunch of these really nice thick pieces of printed circuit board here with some terminals And we matched ball terminals and some metric stainless steel screws. So this is all stainless hardware with these points. And what we're going to end up doing, let's see if I can grab the board out of there, is in order to control the discharge voltage, the nice thing that we got in our eBay purchase is that these two boards are mirror images of each other. So we can put them on hinges, and by placing the ball electrodes between the already positioned points on these boards and the spacing, which is already 30 kV, same as our capacitors, we can adjust the discharge gap and control our output voltage and our output power. So we're going to be reconfiguring all the capacitors that came on here, and I think we've decided on a 960 kilovolt system that gives us 2 capacitors per set, so it's just banks of 2 caps all in series all the way up. And this is what we're considering for the Podkletnov impulse discharge. So our two
I cannot hear Jeremiah at all.
We hear you, Jeremy. What's up?
I can't hear you at all. You need to be mic'd up.
Can you hear me now?
Much better.
Okay, it's the lapel mic then.
Why don't you just grab mine?
Why don't you just shut yours off and I'll turn mine on because it's already attached to me.
Oh, okay. It's been turned off. Okay. I'm sorry about that. Technical difficulties.
Can you hear me? Or am I still coming through quiet?
I can hear you.
Okay, cool. Then that's good enough. Yeah, so our two options for our Marks generator are we can use 64 of our capacitors. That gives us a total of 28.8 joules of discharge energy, 960 kV impulse. Now, the advantage of a higher voltage in the Podkletnov impulse discharge experiment is that any distance between the superconducting emitter and the target electrode, we can get a slightly farther distance. We can get a larger quantity of electrons in that plasma stream because of that greater distance. And also we have a higher electric potential that's immediately presented from the Marks onto the surface of the superconducting emitter. So we are thinking about going with a higher voltage just so that we have some wiggle room in order to guarantee we get a nice even surface plasma discharge, because we want that initial high voltage impulse. And we don't want it to get stuck in just one plasma stream. We want that current to expand wide enough with enough potential behind it where we have a quantity of electrons available to cover the full surface of the superconductor and guarantee we get current flow through any flux pinned regions that are already present. The other option was that we could use 72 capacitors and get a slightly higher discharge current and a total energy of 32.4 joules. And that would limit our output voltage to 720 kV. It would make the Marks generator slightly smaller, and because it's physically smaller, the distance that electrons have to travel through the whole circuit would be consequently shorter, which would give us technically a slightly faster impulse. So even though we only have a small difference between 28.8 and 32.4 joules of discharge energy, we should have, with this configuration, because it's physically smaller by 1/4 of the total length, we should have a consequently faster wavefront. So we're still negotiating that. We think we're going to go with the higher voltage, but we would certainly appreciate input from any of you as far as what's going to happen in the vacuum chamber and whether or not we need better current or higher voltages in order to achieve that even surface discharge plasma that Podkletnov talks about as a necessity for making the gravity impulse work. The other thing we have, just to kind of go over it, we have some YBCO superconductor. According to Poor and Podkletnov, they were custom-made superconductors that both scientists used, and so we're using commercial superconductors. We're not sure if they're actually going to be suitable for a proper replication of Podkletnov, but we're going to go ahead and go through the motions and do everything as if we had the right superconducting material so that we can get set up for it. That way, the only thing that we have to do is mount our superconducting emitter if we need one custom sintered. Electrically bonding the superconductor to the surface, we found out about the bilayer effect thanks to Power, and how you have these Josephson junctions inside that superconducting material by injecting certain insulators, dielectrics, or other materials into the mixture. And so we have to figure out how to properly electrically bond our superconductor to our Josephson junction material, whatever we choose to use. And in this case, we're going to use indium, we think. We tried with gallium live on air the other day, and it was a terrible disaster. The gallium did actually stick when we applied some pressure with some electrical tape on the outside just to sort of pull the two pieces together. But ultimately, gallium is its rate of thermal contraction versus the copper that we use to bind and the superconductor. They're all far too different from each other, and it peeled away. So,
that happened right at supercritical levels, like literally
it happened
right
about
there.
10 degrees just before we hit supercritical. So it held up pretty well for most of the part, but once we got down to the real low temperatures, something broke it off. So we're going to try indium instead. Indium is apparently a much more common used material. It also doesn't tend to eat into metals, which is why it's used in laser diodes with gold surfaces, so it doesn't eat through the gold and cause an electrical contact issue. Then we have to work on a vacuum discharge chamber. In this case, we're just using an acrylic tube. We're going to use a 1/2 inch thick wall, 4-inch diameter, cast acrylic piece, probably about 2 feet long, so that we can see the inside of the chamber and watch our plasma discharge. We think this is really important because, according to Podkletnov's papers, the shape of the surface of the plasma discharge coming off the superconducting emitter determines the consequent intensity of the gravity impulse. And so he was reporting that what happened is a almost cylindrical-like form came off as a plasma from the surface of the superconducting emitter. And if we don't actually see that in our application, then we know we have not faithfully replicated based on the reported information in his paper. So that's something else that we're going to do. We think we figured out the bilayer alternative thanks to POR. So we're going to work on that too. This is where we're at with Eugene Podkletnov stuff. And then the other thing that we're really excited about this month is replicating Richard Van Durk's complex electric field systems, because he's got 2 great alternatives that he talks about. Last APEC meeting, he blew my mind and probably many other minds, because he presented the mathematics and the necessary systems to talk about what happens to electric charges in different frames of reference, and how you can derive a non-zero force from a solid body where you have electric charges flowing in different frames of reference or electric currents flowing in different frames of reference. So we're going to go ahead and replicate one of Van Durk's older systems. He has a rotary disk system that uses 2 physical disks. One moves, one doesn't. One is called the dot product disk, and the dot product disk here is made of very small particles, usually microspheres, of some conductive material suspended in epoxy or situated in such a way that when these tiny little microspheres are charged up and you feed them with an electric potential, that when there's a very small change due to a relativistic field being applied to them, the change in their potential does not have the ability to jump over and conduct current. So basically the charge stays on these microspheres, it doesn't leave them. And as a result, they're able to experience a non-zero force. So our dot product disk, we have some new epoxy. Where is our epoxy?
Right there in the epoxy box.
Great. I'm going to pull that down.
Get the shrink
Especially because Richard is, in the audience today.
Just pull the whole box down.
I think I'm going to open this up and pull out the data sheet here. Epoxy cast 670. So this is an incredibly thin.
No, that's not the.
That's not stuff here.
690.
Oh, the 690. That's the new stuff we're going to work with. So the 690 made by Smooth On. We're going to try to use this as an epoxy. It's incredibly thin. Trying to see where our centipoise rating is on our sheet. Either way, basically, it's mixed viscosity here. Yeah, here we go. 280 centipoise. So it's a very, very thin epoxy, and I think that's going to really help us reach that saturation for our microspheres. We have 3 materials that we can use right now. We have a bismuth powder that's mostly spherical. We have a aluminum powder that should be satisfactory. We have a nickel silver powder. And which is that I pulled out? The magnesium powder that I tested when I just did a pour test to sort of see if you've ever done a fine grinding on a powder and you try to pour out a large volume of it inside of a container, just tilt the container back and forth. If it's spherical, you'll notice that it just seems to flow almost like a liquid. It doesn't act like a powder or a solid, it doesn't bunch up. And so we have some magnesium powder that exhibits that property, and we're going to go with it's mostly spherical and try to inject a very large quantity of that to electrical saturation inside of the epoxy mixture so that we can charge up the microspheres, but then allow them to maintain their charge as we rotate the cross product disk. And so we'll get to that.
Well, what about the bismuth powder?
The bismuth powder is another possibility. And the great thing is we have multiple samples and plenty of epoxy, so we can make many different dot product discs. that are going to allow us to try these different materials and their various properties.
We also have copper powder as well.
Indeed, we do. The copper powder is pretty rough. It seems like it's starting to oxidize if you take a look inside. So I think we might avoid that, or we'll have to do something to it to treat it. So the cross product disc, we just need a very smooth conductive surface so that electrons can freely flow around it. The thinner that surface is, the better it's gonna react. We want to keep them constrained down to that one axis as the cross product disc is rotating. Now, last time Richard revealed a very important piece of information, which is you actually get better results if you rotate the dot product disc. Now that I haven't mathematically comprehended as to why you may get better results if you rotate the cross or the dot product disc, but my thinking was that the dot product disc is going to also experience forces from electrostatic charges on the body of the enclosure that it may not actually, that it wouldn't experience at all if it was stationary compared to the body of the enclosure. So perhaps that's one explanation. The cross product disc is just going to be a CD-ROM that we stuck a voltage multiplier on and blasted off all the metallic coating of it. So we had a nice piece of plastic to work with. And then we laminated that CD-ROM with a piece of thin film mylar using some adhesive and pressed it down with some pressure to get a nice even surface. So we'll be spinning that up to 25,000 RPMs, and we have just another CD-ROM which all the printing was removed from. So we have that metallic coating, which is just a few ohms across the entire surface. That's another good solution for a cross product disc where electrons can travel around it, and you don't get the equal and opposite charges because the electrons are free to move across the surface of the disc.
We also have those really cool hobby electric motors that are capable of like 1 horsepower. Those things are tiny.
Yeah, those are going to give us quite a bit of torque, especially if, according to Richard's paper, what happens is as you generate a linear motion from this system, you end up with a resultant torque on the motor that causes it to slow down, or it loads the motor. So those nice strong motors at high RPM will be able to provide plenty of torque. Not to say that we'll probably ever even come close to loading a motor, because the speeds that we're talking about and the voltage differentials between the dot product and the cross product disc are not realistically strong enough to cause us any significant power draw. It'd be wonderful if we could get materials that would allow us to do something like that, you know, or we could take a 1 horsepower motor, convert it straight to linear momentum and use all that energy. But I think we're a long ways away from that yet. Now, right now, we just want to test it out, make sure that we understand properly what was presented, what Richard's theory implies, and how to actually implement it. And then we want to try our best to try to do a proper Eugene Podkletnov discharge, making sure that our experiment and the observations we make match the observations in the paper. And thanks to the papers that Tim sent over, we have lots of information from POR, which is effectively on the same thing, which we now can use to derive what's going on with Podkletnov.
Right. Talk a little bit about the rectifier tubes. We have a couple of different options on those.
That is a good point.
Some of them are still on their way. They're coming from Russia, I think, the 400 kV ones. We have a couple tubes up there. What kind of tubes do you think we need for this?
So what we ended up ordering is we took a look on eBay and tried to find some reasonably high voltage tubes, because when Ben Durk produced his patent, in his patent he talks about using several kilovolts, and we wanted to try to really push the boundaries of what the dielectrics could take. So we're going to try to go into the double-digit kilovolts, and in order to do that, we needed some double-digit rectifiers that could handle that voltage. So we ordered some from Russia. They're coming in, and those are going to allow us to isolate our electrical power supply or our power source from the physical device itself, so that electrons can't backflow. And if there's an imbalance due to the changes in the electric fields from the complex electric field interaction, that we're not going to have electrons flowing into or out of ground or the power supply to try to neutralize out those changes in potential. So we're going to use rectifier tubes. We're going to power them off 18650 batteries or other small LiPo batteries, so that we can completely isolate that system and properly test what Ben Durk has presented.
Right. Also, the oscilloscopes and any test equipment that we plan on attaching to this experiment is also going to be floated using a UPS system, completely separated from ground, because I know that's very important.
It was that big eureka to realize that most of the reasons why we were having problems and erratic results had everything to do with the fact that we always had some kind of leakage or connection to an earth ground. And that caused us major issues, because an earth ground, effectively an electrical connection between 2 points in any system, ties those two systems together into the same frame of reference. And it's wild to think that you can connect different frames of reference with a piece of wire, but that's effectively what you're doing. So you have to keep them isolated, and to finally have learned about that and realized why we've seen some effects anomalously in very fast systems where the resistance of our electrical connections was actually not sufficient to totally separate out the frames of reference. That's why we've seen the effects. It was a big eureka to realize why. And again, huge thank you to Richard for presenting that so we finally understand.
Okay.
Yeah.
Also,
yeah, I've been listening here, and I probably had a couple comments on what you had to say on this.
Yeah, please.
You had a question on rotating the dot product disk.
Yeah.
Yeah. So what you want to do is, one of the things the dot product is generating is a scalar potential. So when you rotate it, you're effectively taking the charge and accelerating it 90 degrees to its relative motion. Well, that causes the scalar potential to basically decouple from the potential. So it'll build up around the individual particles as, say, you rotate them. So that's the reason why you really want to rotate the dot product disk too, because you're going to end up starting to build up the scalar potential. And then that actually, the experiments we've done recently seems to show that that has a much greater effect than the cross product disk. So if you can, that would be a desirable thing, is to get your dot product disk all balanced out. And if you can rotate that in the opposite direction as the cross product disk, I think you'll have a better effect. But yeah, it sounds like you're doing everything correctly. Just make sure you don't get any past the ground. And I think you should start seeing some good results. And of course, you'll let me know when you start putting it together, right?
Absolutely, Richard. I mean, you're the reason why we're doing this particular experiment, and what you presented was, as we said, a huge eureka. It just is it's a total difference in understanding why some things happen the way they do, because we've seen strange effects for a long, long time. I've been doing this for now going on almost 22 years. And I've seen a lot of really, really weird things happen, especially around very high currents with capacitor discharges, around very high impulse voltages. And I've noticed a trend with these various things that I've seen with objects moving on their own, or electronics being triggered by an EM pulse that should have never existed from the amount of power that we had, but it seemed to go a really, really long distance. It finally makes a lot of sense as to why you could be generating scalar potentials and how they can transfer. Because the great thing about a scalar potential, right, is that you can't really block it. It's a point, or it's a charge that's going to expand out, and that charge field is going to have an effect on all other objects. You can't really block a change in local electric potential from one potential to another. It's going to penetrate, and that gives us the unique ability to change the field geometries of that generated signal source and screw around with scalar potentials in a way that I don't think we've ever even realized we should be looking into.
Yeah, and that seems to be the key here, is those scalar potentials. Once you're able
to read the live chats,
they'll persist there for a while too.
Yeah, Jeremy, go ahead if you have live chat questions.
I can't hear you.
Jeremy, go ahead if you have live chat questions.
Your sound just went completely dead. I can't hear anything.
Oh, did it turn
off? No, it says it's on.
Yeah, I can still hear you guys fine.
I'll just stay close to Mark's mic, I guess.
That's better. I just came back.
So live chat questions, Jeremy?
Over here we have our power supply racks. Just want to show you this real quick. This is for the Alzofon experiment. This is a 30 volt, 40 amp, or a 40 volt, 30 amp power supply. It's one of the really old kinds, super heavy, had to ship freight. That's to supply the super stable laminar magnetic field for the electromagnet. Up on top over here, we have a Maxwell 45 kV. This came out of Sandia Labs, used equipment. It's 45 kV, 8,000 watts, and I managed to get the matching capacitors, also 45 kV capacitors here locally. So that is for the lower voltage version of the impulse experiment with Podkletnov with superconductors. In order to read everything, we got this out of Singapore. It is 16 gigacycles per second scope. the only way we could afford a scope this fast is by getting a super old one that still works. And as you can see over here, we actually had to buy these, I don't know if you guys can still remember these things. These are coming out of museums, floppy disks and a floppy drive in order to read the data. But the scope still works, and it probably costs as much as a small house when it first came out. Over here we have, this rack is really the super high voltage rack. There's a scope attached to it as well, which we had to shield from our last experiment. This was for testing the capacitors. But basically this rack has a gamma 125 kV 5 milliamp power supply, and below that is a 10,000 to 1 voltage divider, and that's hooked up to that oscilloscope. So we're able to see high voltage potentials on a standard oscilloscope. We could also hook that up to our 16 gigacycle per second oscilloscope to measure the impulse velocity rates, for any of these high voltage, high current experiments. And that's most of our equipment right now. We have also in this corner, this is something that Jeremy brought in. This is a 5 kV half amp power supply that's going to be used for the klystron. Jeremy actually found that on Craigslist from a lab that was going out of business, and this is something that we couldn't find anywhere else. So it was amazing that he was able to bring that down to the lab for us. And we're currently working on that. I think that we're going to have to bypass one of the safety relays in order to just.
Yeah, we're going to bypass the interlock.
I just want to comment on how heavy that thing is.
Yes.
Oh, yes.
How did you get that into the car on your own?
That thing is very heavy.
I think I had help. I had to get help. I could not have moved it by myself. No, I did have to have a second person help me move it and transport it.
It's got a huge plate transformer in the bottom. That's a beast.
You can see the front dials. Look at the size of that dial. That's my hand.
Yeah, that's some like 1940s old school equipment. That thing's diesel. That thing's built. You don't find equipment like that anymore.
Yeah, so I think this is the interlock. There's the problem with the that transformer is blown out. It's a 12-volt transformer, so the interlocks are not working. So we could either replace the transformer, or we could just override the interlock. It's something that we're considering.
At its core, all that thing really is effectively is a voltage divider for some meters and current, a variac, and a huge plate transformer that has multiple wiring configurations. And all we have to do is give that variac power to feed the plate transformer. The rectifiers are already in place, and everything else should pretty much work straightforward. There's no reason why we need an interlock in that system if we're going to install it in a cabinet and bring out external cables anyways. We're going to be setting it up in our lab, and we have sufficient signage to indicate the dangers of the system.
And something else that was really cool that he got from that same lab, they couldn't explain it to Jeremy why they had it, was a whole bunch of waveguides that were tuned to a very specific frequency of 6.21819 gigahertz. And there's a ton of tuning that went into all these waveguides. There are several pieces of waveguide all tuned to a specific frequency. And that will work wonders for our experiment, because if we can lock the frequency in at a certain point, we can just use this power supply over here to change the flux in the magnetic field, and use that as our variable to finally find the low more precession frequency by changing the magnetic field strength.
Well, that's pretty much the summary of what we already have going on. We are planning on a few other projects that we haven't really written up yet. These are the focus points right now. We don't want to get our hands in too many baskets. We want to focus on the projects at hand, which is Podkletnov and Richard Ben Durk. So if we can get far enough along on either of those that we can make progress, then we'll move on to a few other projects, perhaps this month or the following months. But that's the update from the Falcon Space Lab. That's where we're at right now. We're testing everything that we can, and we're focusing on the things that we think that we have at our current skill level and our reception with the communities, things we can actually do and test properly. Because we're not just trying to put together things that look kind of sort of similar to what the scientists did. We want to replicate as accurately, as faithfully as possible.
Exactly. That's the most important point, is to be able to actually replicate them in the lab. And I'm also excited about the Alzofon thing. I have been working on it for a while, but we need to figure out the waveguides. Until we figure out the waveguides, it's all just a waste, you know.
Yeah, the real trouble we're having with waveguide issues right now is that we can beam out that signal at whatever frequency we choose from our frequency sources, but that signal is basically hitting the sample and then flying past it and being lost in attenuation to the outside environment. So what we need is a resonant chamber that we can tune for the frequency ranges that we're using, which is the 8.8 to 9.5 gigahertz range. And then we need to design something else perhaps more powerful for our klystrons range. So that way we can get a nice Q factor. We can get many, many times more power into the sample so that the sample itself absorbs that microwave energy instead of it just being lost in the environment or causing us SWR issues down the line.
Yeah, and just reading SWR on a microwave waveguide, I mean, there is no microwave waveguide SWR meters out there. It's literally something you have to build yourself. And we're talking to all the professionals in the field. It seems like it's a real specialty. There's very few people who understand this stuff to the level.
Sort of an industry secret, hey?
It's an industry secret, yeah.
Like, how do you design a proper waveguide with an incredibly high Q to get energy into a sample?
How do you measure the Q in the first place? And how do you measure the reflected energy? These are all issues that we're going to have to work on.
Not stuff that you can easily Google, because I've spent many hours on there trying to find this stuff out. But unfortunately, it seems like it's just it's a bit difficult. Maybe it's because we're just ignorant of the right terms to use. We may not be looking up at the right information, or
we don't even know the question to ask.
Right, exactly. We don't know what we don't know. So this is definitely where we're asking for help to try to figure this problem out, so we can test Alzafon properly and get energy into the sample to see if we get good dynamic nuclear orientation and we get good coupling from our microwave energy into our sample.
In terms of capabilities, we also have a 3D printer over here that we can print in resin that we can then cast in any different metal. We have furnaces and we have casting materials. So if you want to cast something in silver, nickel, or bismuth, we purchased a whole bunch of bismuth. It has a high spin ratio. It's a pretty interesting metal. We thought it might be interesting to try something with bismuth. Now, also you have the bilayer setup that was found as a supposed relic of a flying saucer. And if there is something to bismuth mixing with other metals in a bilayer that we can put into the Alzofon experiment, that's something I really want to try. So any help from the community, anyone who knows anything about these experiments or knows somebody who knows how to work with microwave waveguides and tune them properly, that will be very beneficial to what we're doing over here. And like I said before, we do have some limited funding from an anonymous donor, and so far they've given us around $30,000, and this is what we've been able to put together with that. We have more equipment coming in the mail. We also have a guest house available, and he's offered, like, if there's any scientists who have relevant information to the experiments that we're doing, he's glad to fund them to fly down here, all expenses paid, and we can work on these experiments in this anti-gravity lab right here live. And all of these videos, all of these experiments, by the way, are going to be published live on YouTube. Jeremy Reese and Travis have worked out a system with multiple cameras. You can see our first demo of that, where we kind of made a makeshift experiment just to try it all out. And that was really amazing how we were able to get all the cameras together and run an experiment live on YouTube.
Okay.
What happened?
All right, I just want to remind everyone to smash that like button who's watching this live, and share this video with anyone you think who might be interested. Again, we're going to be making like short clips of highlights and of key points and things. And again, we invite anyone from the audience who has information they'd like to present and join this community, anything that could contribute to the body of knowledge, or the lists of or the experiments in the lab, anyone who has equipment or anything else like that, or time or lab time that they can offer to run certain experiments, or if they have, they can help us run these experiments. Basically, like, the goal is to bring more and more scientists on who know stuff about this, share the information in an open atmosphere, and kind of accelerate the process of R&D and disclosure, really, of the information. Because people think there's a lot of people talking about disclosure right now, but I don't think they're really willing to learn the real information and put the time into to really wrap their head around this kind of knowledge that's going to take to build the first craft that gets us off this planet. That's really, the goal here. I know it seems like quite a achievement for some of the people out there, maybe thinking like this might be 5, 10 years, 20 years. This might take our lifetime. These guys have been working on it for quite a long time already. And that's awesome that they're here to share all of their knowledge and experience with us. There's no better teacher than failure, I say. And the more that we can demonstrate all these other experiments of the past in a lab setting with a group of people that are really real skeptics, that people that have a track record that people can trust, if we can vet these out in our own lab publicly, one at a time, it will save so many people so many wasted time or years of wasted time and their own wasted research and funds and everything, because there's so many videos on the internet showing these kinds of things. And if we can show them and really vet them out and say, like, this doesn't work, this doesn't work, this doesn't work, that's going to help save a ton of people's time. And if anyone out there has already done these experiments and knows how to set them up, or has them already set up somewhere, they can go and show us, okay, we've tried this didn't work, this didn't work. That's really where we need to go through, because and do is prove to people that no, they're at the same time, it's going to vet out the whole people like Stephen Greer, who claim that there's a secret space program that figured this all out back in the 50s. And if that was the case, I don't know what the heck you guys were doing working for DARPA on all this stuff for the past 50 years, if they already figured it out in 54, like Stephen Greer wants to tell everybody. Again, if they did, we're going to figure it out. We're going to find it. But if not, and this really is the cutting edge in humanity's evolution to the stars, then we're going to hopefully put the laboratory and the team and the scientists together to bring disclosure on that level. And hopefully the scientific community is open to that, and open to contributing with us, not just, the naysayer, that there's naysayers that just want to fight everything and say, oh, you're not going through the conventional channels and stuff, like this guy was saying in the live chat. You should be doing peer review. Peer review will come. Like when we get something that is actually works and is worth, writing a paper on, I want to definitely write papers with you guys. And we have a team of people ready to do that when our lab does have success. I want to write papers and publish it in the peer review and get it out there. But we also have a kind of a fear and a skepticism of that whole process, that, that whole system has been used to suppress information like this in the past. So we want to do it publicly first, demonstrate it and show people how to do it and whatever works, show people all the stuff that doesn't work. And then when we get it, we know how it works. We want to have led up to it and people who have followed it to really have the knowledge and the background to understand the science behind it when we do have that success in the future. And I really have confidence that we will, with this team and the amount of people that are coming out of the community and bringing us support and hope.
Can you guys hear me all right?
Wonderful. Yes. And
you're a little quiet.
Wayne has his hand up also. I should mention that.
Yeah, Wayne, go ahead.
Yeah. Hey. I just wanted to do to share a couple little things that I've been working on and will be working on in the near future. And it relates a lot to what Todd was sharing about the NMR and what you guys are working on and have worked on with Alzofon and all that. So I've been thinking about how to maybe work this thing at lower frequencies. So just using these, I made this last night. So this is going to be, there's going to be two Helmholtz coils oriented perpendicular to each other. So the one will produce kind of a weak magnetic field. I'm aiming for about 30 Gauss. And then I'm going to have across from that perpendicular, I'm going to have RF. Well, it won't be RF, something around the 20 kilohertz. So I'm aiming for around the audio frequency range. And I'm going to put some, I kind of calculated it to work with bismuth because I have some powdered bismuth I'm working with. And so I just put the sample in there and maybe suspend it. So that's something interesting. And then here I had inside here between these two neomagnets is an epoxy casting with bismuth powder in it. And so I was and will be playing with that, putting some AC magnetic fields in here and just putting it on a scale and seeing what happens with that. Here's an older Helmholtz coil I made. And yeah, so this here is a capacitor I made. It's got bismuth powder in the middle with epoxy and dielectric. And I was going to test it with different, like high frequency, high voltage currents. I'm thinking that might excite some effects inside the bismuth atoms. So yeah, I just wanted to give a little quick update. I'll be posting all my stuff on my YouTube channel, Fail Forward Research. And yeah, that's about it. Thanks.
Yeah, let me compliment you on the quality of your builds now. I mean, they're looking really, really good. You're spending a lot of time putting them together as compared to the earlier experiments where we sort of crashed course our way to figuring this stuff out. It looks like you're trying to up your game, and that's awesome to see.
Yeah, I don't have a lot to work with, but you know, I'm trying to do the best I can. So yeah, there's a long way to go. There's a long way to go. Yeah. But,
great job, Wayne.
yeah, thanks guys, and look forward to all of what you're working on there. That's going to be amazing.
The other thing that I wanted to point out for sure, especially amongst this community, is once we build this equipment, you know, we may not be the biggest experts in the industry on exactly how to use it, but we have the equipment. So when we have a 1 megavolt Marks generator, or a 960 kV Marks generator, and you have an experiment that you want tested on it, or an apparatus that you want hooked up to it, I mean, that's something we'd be interested in testing out. So we just want to sort of extend that offer out there to people in this community, where if you have devices that require weird equipment or specialized equipment like the types that we're setting up here, we would be interested in collaborating with you and using what we've already acquired to try and test out your ideas and theories. We can follow them like a scientific procedure and do exactly what you recommend to do to make sure that we test what you're looking for.
Wonderful. Well, gentlemen, do you think we should call it a day today?
Only one way to find out if he'll answer, and I'd say give him a call.
Well, no, I mean, yeah. I think it's probably time for us to wrap things up for today. So
yeah, I agree, and I'm just typing some stuff away and getting some links together. We're going to put some links together for this whole talk. This was an excellent discussion. I learned a lot from our guests. Thank you, Gary, for being part of this, and thank you, Todd, and thank you as always, Tim, for putting this together. And
applause for Tim.
Yeah. Well, Gary, thank you again very, very much. And Todd, you as well. You're hiding on my screen, but I think you're still here. Yeah, there you are. I'm losing. There you go. Okay.
Thanks to everyone who contributed. Anyone wants to give a shout out real quick to the end for a link or anything that they want to give a shout out, they can go ahead and do that. And then we'll go ahead and wrap this up for the day. Fail Forward Research, that's Wayne. I'll give a shout out to him. And then also you guys can check out Join the Technicians, although Jeremiah is not really doing much with that channel anymore. And then I'll post a link to Clay's website for his disclosure project there.
Yeah, and we'll get Gary's material up as well. So, and then I believe Todd
yep,
definitely
Gary,
send me over
I
links.
posted his link already too. Sorry.
Wonderful. Okay, well, thank you again.
I just want to make a shout out to Tim Ventura, who made this entire thing possible. Let's give it.
Well, thank you, sir. Okay, on that note, let me hit the stop button, and we will wrap this one up. This will probably be our last event for 2020. And there we go.